In this video, we're going to look at some problems from the Chapter 5 Review Worksheet. These problems will cover all the concepts in Chapter 5, so let's get started. Number 2, we are asked in this set of problems to simplify these expressions. And so in this case, I'm going to go to sines and cosines on it. So cotangent of x is going to be cosine of x over sine of x. Tangent of x is going to be sine of x over cosine of x. And I am multiplying those two together. After I find out what that is, I'm going to add to it. We have sine of x. And then we have secant of x, which is 1 over cosine. So I'm going to add to it whatever that product is. So let's start with the left side. If I look at simplifying this first, it's all multiplication, which means I cross out common factors in the top and the bottom. So I'm left with a 1. If I look over on the second term, it's really sine of x over 1, and I can just multiply for it. So I get sine of x times 1, which is sine of x. On the bottom, I get a cosine of x. So I have sine of x over cosine of x, which just gives me tangent. So my final answer is 1 plus tangent of x. Now, I'm going to be honest, I took the long way there, and there's nothing wrong with that, because I went to all sines and cosines and simplified. As we go along further, the idea is to start recognizing patterns, and I can notice right away in this that cotangent of x times tangent of x, I am multiplying reciprocals. And when you do that, you get 1. And so I could have used that technique as well to save going to sines and cosines in the first term. Either way, it doesn't matter as long as you get 1 plus tangent x. If I look at number 3, in this case, I'm not going to go to sines and cosines. And the reason why is right now they're squared. That's not the main reason though. The main reason is I can see the first term has a tangent squared and the second term has a tangent squared. So they have a GCF in common for it. They have a tangent squared of x in common. And I can use the GCF, factor that out, and get cosecant squared of x minus 1. Now I see right away that I have a Pythagorean identity here. I see a square trig ratio, and I'm subtracting 1, and I can see cosecant squared of x minus 1 is cotangent squared of x. And so really, I have my first term, tangent squared of x times cotangent squared of x. Same idea. These are reciprocals of the same powers. I'm taking tangent squared times cotangent squared. When you multiply reciprocals, you're going to get 1. So I can see that if I need to and go right into that. But if you can't, you go to sines and cosines. Tangent squared is sine squared over cosine squared. Cotangent squared is cosine squared over sine squared. And I can cross out common factors in the top and bottom, and that also gives me 1. So it doesn't matter which approach you use, but if I can multiply reciprocals very quickly and get 1, that's going to make my life a lot easier. So next, I have number 5. Cotangent squared of x plus sine of x times cosecant of x. So maybe I want to go to sines and cosines. I'm not going to right now. I'll leave this as cotangent squared of x, and we'll see what happens. Well, I have a sine of x, so I'm going to leave that alone, but I'm multiplying by cosecant of x. So that's 1 over sine of x. Well, notice on this second term, you are multiplying. So I have to simplify this. Well, they have common factors in the top and bottom, so those can cross out. So really, I have cotangent squared of x plus 1. And that square trig ratio, a 1 there, maybe that's a Pythagorean identity. And it is. It is cosecant squared of x. And there's our answer. Now, I said in the beginning that I wasn't going to go to sines and cosines, but I could have. I could have changed tangent squared of x to cosine squared of x over sine squared of x. And I would have had the same thing on the right side, sine of x times 1 over sine of x. These would still cancel and would still give me the 1 I want. And I would see, well, there's nothing I can do with that besides change back to cotangent squared. Another path there, it works either way. If I look at number 6, I like problems like number 6 because I see it and I read the problem and I notice it's all multiplication in between my trig ratios, which makes my life a lot easier because if it's all multiplication and I go to sines and cosines for this problem, like I'm doing, I can cross out common factors in the top and the bottom, which makes simplifying really easy. So I have a sine squared of x on top, I have a sine squared of x on the bottom, cancels out. I have a cosine squared on top, but I have a cosine of x on the bottom, so only one of these on top is going to cancel. So really I'm left with cosine of x over sine of x, which can just simplify into cotangent of x. And there's my answer. So let's take a look at number 7. Do be aware that the problem says use the sum or difference identities. So I'm being specific about what formula I want to use. So the first thing we can do with this, if you want, is go into degrees. I can take pi over 12, multiply by 180 degrees over pi. The pi's will cross out, and so then I am left with, in this case, sine of pi over 12 equals 180 divided by 12, which is going to be 15 degrees. So really I want the sine of 15 degrees. And the sum of difference means I want to use angles around the unit circle. I want to create 15 degrees from those. So what I'm going to do is I am going to do 45 degrees and I'm going to subtract 30 degrees. And if I have the difference formula for sine, it is sine, cosine, cosine, sine. And since this is minus for sine, the sine stays the same. So I have sine of 45 degrees times the cosine of 30 degrees minus the cosine of 45 degrees and the sine of 30 degrees. So the sine of 45 is radical 2 over 2. The cosine of 30 is radical 3 over 2 minus the cosine of 45 is radical 2 over 2 and the sine of 30 is 1 over 2. Realize you're multiplying. So when you multiply the tops together, you're going to get radical 6. Multiply the bottoms, you're going to get over 4. Multiply the top, you're going to get minus radical 2. Multiply the bottom, you're going to get 4. They have the same denominator, so the final answer is radical 6 minus radical 2 all over 4. There's your difference formula for sine. The formula sine, cosine, cosine, sine. Now let's try it with tangent. Now tangent is going to be a little bit more difficult for the sum of difference formula on it. I want to create, in this case, 165 degrees. Now I can use sum or difference. It's just how your mind works on how do you create 165 degrees. And for me, what I'm going to do is I am going to take, for this one, 165, I'm going to do 120 degrees plus 45 degrees. Now there's a variety you could choose from, but these are the ones I'm going to use. Now the formula for tangent sum is tan, tan, 1 tan, tan. So tan, tan over 1 tan, tan. And I'm just going to plug in, the sign stays the same on the top and it changes on the bottom. So there's the structure I have, and I'm just going to plug in my angles, which we have 120 degrees, and then we have 45 degrees. So it's going to be the same thing on the bottom, 120 degrees, 45 degrees. And I'm going to simplify the top and the bottom separately for this. So the tangent of 120 degrees is negative square root of 3. The tangent of 45 degrees is 1. Now I'm going to do this part off to the side. They're the same right here. Tangent of 120, just like before, which we said was negative radical 3, and tangent of 45, which is 1. And we are multiplying those. So I have 1 minus a negative square root of 3, but we don't write minus and negatives, we write plus. So since I have 1 minus a negative radical 3, it's 1 plus radical 3 at the bottom. Now in this case, we cannot have a square root in the denominator, so our job is going to be to rationalize this denominator. And we do that by using whatever the conjugate of the denominator is. So in this case, the same terms, opposite signs. So 1 minus radical 3 and 1 minus radical 3. Now, unlike in previous videos, I'm going to kind of take my time for doing this for those who are struggling with the idea of conjugates. And I'm going to do it by using the box method for multiplying. I'm going to do an n for numerator. So the numerator is a negative radical 3 and a positive 1. And I'm multiplying that by a 1 and a negative radical 3. So let's fill it in. I have 1 times negative radical 3, which is negative radical 3. I have 1 times 1, which is 1. And negative times a negative is a positive. And then radical 3 and radical 3 is 3. 1 times negative radical 3 is negative radical 3. And I can use these boxes to simplify. The 1 and the 3 combine to give me a 4. The negative radical 3 and the negative radical 3 is a negative 2 radical 3. So my numerator is a 4 minus 2 radical 3. And I could do the same thing with the denominator, d for denominator. I can set up that multiplication by using boxes as well. I have a 1 and a positive radical 3, and I have a 1 and a negative radical 3. 1 and 1 is 1. 1 and radical 3 is radical 3. 1 and negative radical 3 is negative radical 3. And negative times a positive is a negative, and the radicals are going to cancel. Again, combined terms. 1 minus 3 is negative 2. And then these two are opposites, so they're going to cancel. So my denominator is just a negative 2. So I could see that these two can be divided by a negative 2. They have that in common. So I'm going to take 4 divided by negative 2, which is a negative 2. And I'm going to take negative 2 divided by negative 2, which is a positive 1. So that's a positive radical 3. And there's my answer. So this is the first time I kind of showed the box method in one of the videos. I think it helps organize for those of you who are struggling with conjugates, the simplifying process for it. Let's take a look at number 9. We are asked to find the exact value, given that you are in the first quadrant, of sine of x minus y if you're given these ratios of right triangles. So what I'm going to do is I'm going to draw my right triangles. For a right triangle in quadrant 1, with an angle of x, you have a sine opposite of 4 and hypotenuse of 5. And so I can use the Pythagorean identity for this, Pythagorean theorem. I would have a squared plus b squared equals c squared. And so that would mean a squared of 9, which means my adjacent side is 3. So I'm going to use this, and I'm going to state what's sine, what's cosine for this triangle. Well, I was told sine of x is 4/5. And I can find now cosine of x is 3/5 on it. If I want, I can do tangent of x is 4/3. But I'm just going to deal with the sine and the cosine for it. What we're going to do next is look at the next triangle. The next triangle I have cosine of y. So I'll draw a triangle y in the first quadrant, like it says. 12 is my adjacent, 13 is my hypotenuse. Same thing. Pythagorean theorem, a squared plus 12 squared equals 13 squared. And I'll get a squared as 25, which gives me a side of 5 here. So the sine of y is 5 over 13, and the cosine of y was given to me as 12 over 13. Now the reason why we use these is because if I were to break down the difference formula, it's sine, cosine, cosine, sine. And it's the same sign as the problem, so it's difference. And it's sine of x, cosine of y, minus cosine of x, sine of y. And because I did these triangles, I now have sine of x and cosine of x. I now have sine of y and cosine of y. So I have everything I need. Sine of x was 4/5. Cosine of y was 12 over 13. Cosine of x was 3/5. Sine of y was 5 over 13. So if I multiply, I'm going to get 48 over 65 minus 15 over 65. So my final answer is 33 over 65. And so that is the value of sine of x minus y given that scenario. So in this case, I drew the pictures first and I did the formula second. Notice I have number 10 here. We'll go the opposite direction. I'll do the formula first. Cosine of x plus y, that's going to give me cosine, cosine, sine, sine. So cosine, cosine, sine, sine. And the operations change, so this one's going to be a minus. So I have cosine of x, cosine of y, minus sine of x times sine of y. So I have all the information I need for my formula. The problem is, though, I can't do anything because all I know is cosine of x. And all I know is sine of y. I'm missing two of the trig ratios. And so that's why we draw a triangle, is I don't have all the information, but maybe I can find it. So I'm told the cosine of x is 1/2, so my adjacent and my hypotenuse. So a squared plus 1 squared equals 2 squared. That's going to be a squared of 3. So I get radical 3 here. So my sine of x is radical 3 over 2. And my cosine of x is 1/2, which was given to me. I'm going to do the next triangle. I have my triangle for y. I'm told my opposite is 7, my hypotenuse is 25, so a squared plus 7 squared equals 25 squared. And so in this case, when I'm doing it, I'm going to get a squared equals 576, so a is 24. So I know the sine of y is 7 over 25, and the cosine of y is 24 over 25. And so now I have all the information I need. I was missing cosine of y, I found it. I was missing sine of x, I found it. So we are good. I have all my information for plugging in based off of drawing my right triangles. So I know the cosine of x, and the cosine of x was given to me as 1/2. Well, now I want the cosine of y, which is 24 over 25. And I'm going to subtract the sine of x, which I found to be square root of 3 over 2. And the sine of y, which in this case is 7 over 25, which was given to me. So now if we multiply, we're going to get 1 times 24 over 50 minus, in this case, I have 7 radical 3 over 50. Now I can't do anything with this, so I am going to leave them alone and write it as 24 minus 7 radical 3 over 50. There's my final answer. So we move on. We have numbers 11 and 12. Both of these, again, look at the directions. This one's asking us to do the half angle theorem. And so right away, I know I have to use one of those. I'm going to take my degrees like I did before, and I'm going to start my radians, and I'm going to change them into degrees. I'm going to multiply by 180 over pi. And so the pi's cancel. If I do 3 times 180 and then divide by 8, I'm going to get 67 degrees. Now this is not in our trig chart. 67.5 degrees is not a nice value around the unit circle. So really what happens is when I want to use my formula, that's half of the angle I want to use. And so I need to figure out what is the alpha for this. So I have alpha over 2 equals 67.5 degrees. And so if I solve for the angle I want, I'm just going to double it. And so in this case, I'm going to get 135 degrees. And that's going to be the formula I use. Because the formula for the half angle theorem for sine says that you have sine of alpha over 2, it equals positive negative square root of 1 minus the cosine of alpha over 2. So that's the formula that we're going to use and we're going to go through. So I have all my information. Let's figure out what we do. So my alpha we found was 135 degrees. And so I'm going to take, and if I look at it, just to kind of so you can see how the formula works, you have sine of 135 degrees divided by 2. And I'm stopping there because that is 67.5. That's what alpha represents, is double the number we're working with. So it equals plus or minus, and we'll get there, the square root of 1 minus the cosine of our alpha, which is 135 over 2. Now, I said we're going to get there is we have this plus or minus there. What that means is what quadrant is our original angle in? All students talk constantly. Our original angle is 67.5 degrees. That's in quadrant 1. And so therefore what we want is we only want the positive. We don't deal with the negative. This is based off of what quadrant we're in. And so I'm just going to remove this so I deal with the positive. And let's just go to our chart. We have square root. The cosine of 315 degrees is a negative, a negative radical 2 over 2. And 1 minus a negative is really a plus. So I'm going to change this to 1 plus square root of 2 over 2. So since this value is negative radical 2 over 2, that changes it to a plus, and that's all over 2. Well, right away, I need to realize I have to simplify the top, and that needs a common denominator. So 1 is really 2 over 2 plus radical 2 over 2. So the numerator is 2 plus the square root of 2 over 2. And again, we still have that large square root. On the bottom, I still have that 2. Now, when I flip and multiply, because I'm taking a fraction and I am dividing it. So when I flip and multiply, what's going to happen is I'm going to end up with a 4 on the bottom. So I have the square root of 2 plus the square root of 2 over 4. And when you square a fraction, you square root the top. So we're just going to leave that top alone, and you square root the bottom. And so the square root of 4 is 2. And there's our answer. It looks nasty, however, that is the actual answer for the sine of 67.5 degrees. We do the same thing for tangent. It is 22.5 degrees. That's my alpha over 2. It's half the angle I'm looking for. So what I'm going to do is I'm going to double it. And that's going to give me 45 degrees. And so I want, really, if I want the tangent of 22.5, I'm going to take tangent of my 45 degrees, which is my alpha, and I'm going to divide by 2. The formula for alpha over 2 is 2 of them. You can either do sine of alpha over 1 plus cosine of alpha, or you can do 1 minus cosine of alpha over sine of alpha. And it doesn't matter which one you do. Personally, I'm going to look at my trig chart, and I'm going to take a look. The sine of 45 degrees is radical 2 over 2. And the cosine of 45 degrees is radical 2 over 2. Which denominator do I want to work with based off of radical 2 over 2? And personally, I want to work with just one term on the bottom. I want to work with this one. It's going to be easier not to add in the bottom, but add in the top. So I have the tangent of, in this case, 45 degrees divided by 2 is what gives me 22.5. That's 1 minus the cosine of 45 over the sine of 45, which, by the way, I already wrote off to the right. The cosine of 45 is radical 2 over 2. And the sine of 45 is radical 2 over 2. Again, notice the top needs a common denominator, and I'm going to do that first. And the common denominator is not hard for this case because 1 is really 2 over 2. So I have 2 over 2 minus radical 2. So if I keep going, I'm going to have a 2 minus radical 2 over 2. And I still have this denominator here. all over radical 2 over 2. And I have to figure out what to do. Well, I'm going to flip and multiply. When I flip and multiply, these are going to cancel. So right now I have a 2 minus square root of 2 all over square root of 2, which I can't have a square root at the bottom, which means I have to rationalize. So I'm going to multiply by radical 2 over radical 2. And that's going to give me 2 radical 2 minus, and then radical 2 times radical 2 is just going to cancel, so that's 2. So 2 radical 2 minus 2 over, well, here the radicals can cancel, so 2. And again, notice all my numbers here are divisible by 2. So I get square root of 2 minus 1 over 1, which is just this. So in this case, I use the formula with the sign of alpha on the bottom. And no matter what, if I use the other formula, I would have had to rationalize as well, but I would have had to use the conjugate. So if I quickly write up here the other formula, it was sine of alpha over 1 plus cosine of alpha. I will tell you 90% of the time I use this formula. And the reason why, there's only one term in the bottom. And so it's a lot easier to flip and multiply, and even then it's a lot easier to rationalize with one term. This 1 plus cosine of alpha, I only use this formula in 2 cases. If my cosine of my angle is a positive or negative 1/2, that is the only time I ever use this formula. Because then it's easy. 1 plus 1/2, 1 minus 1/2, not difficult. That's the only time I ever do this one. Every other time you'll see me use this formula. So let's take a look at 13. For 13, we're asked to find sine of 2 theta, cosine of 2 theta, tangent of 2 theta. If we're given cosine of theta is 2/7 and it's in quadrant 4. So always pay attention to what quadrant you're in. Quadrant 4, if I have a cosine of alpha of 2/7, my adjacent side is 2 and my hypotenuse is 7, I'll be able to do the Pythagorean theorem for this one. Is I'll get a squared plus 2 squared equals 7 squared. So a squared is 45. A is the square root of 45. Which when you simplify, you will get 3 square root of 5. However, you're going down, and so that'd be a negative 3 square root of 5. So I'm going to draw my picture, and I'm going to draw it in the appropriate quadrant. I'm going to be careful of the direction that I'm going for this. And the reason why is this is going to allow me to find all the values I need. The formula for the double angle theorem with sine of 2 theta equals 2 sine of theta cosine of theta. Well, I have my entire right triangle now. So I know the sine of theta is negative 3 square root of 5 over 7. The cosine of theta was given to me as 2/7. I could even do the tangent of theta. Tangent of theta is negative 3 square root of 5 over 2. So in this case, I just need the sine and cosine. So it equals 2 times the sine of theta, which I have as negative 3 square root of 5 over 7, times the cosine of theta, which we have as 2/7. So this is straight multiplication. 2 times negative 3 times 2, that's going to give me negative 12. And at the bottom, so negative 12 square root of 5 over 49. And so that is the sine of 2 theta. Pretty straightforward double angle theorem with sine. We can do the same thing for cosine of 2 theta. Now cosine of 2 theta has multiple formulas. For this one, I'm just going to do the one that says cosine squared of theta minus sine squared of theta. Seems to be the one most students are using. So I have 2/7 squared minus a negative 3 square root of 5 over 7 squared. So if I square the top, the numerator, and the bottom, the denominator for both, I'm going to get 4 over 49 minus, and I'll do it off to the side, negative 3 squared is 9, square the square root, and you're just left with what's inside. Square the bottom, you get 49. So I'm going to get 4 over 49 minus 45 over 49. And that's going to give me a cosine of 2 theta equals negative 44 over 49. So there's your cosine of 2 theta. Again, pretty straightforward, easy to use. Now for tangent of 2 theta, you could use the double angle theorem formula for tangent of 2 theta, which it says twice the tangent of theta over 1 minus tangent squared of theta. And I have no problem with you using that. Good for you. Have fun. Personally, I like less work. If tangent is sine over cosine, then tangent 2 theta is sine of 2 theta over cosine of 2 theta. And I already did all the work for sine. It's negative 12 square root of 5 over 49. And I already did all that work for cosine, which is negative 44 over 49. When you flip and multiply, these cancel. And a negative divided by negative is a positive. So you get 12 square root of 5 over 44. And that is the tangent of 2 theta. Pretty straightforward approach for tangent 2 theta if you use the definition that tangent of theta is sine of theta over cosine of theta. So you can logically do the same thing with 2 theta. And we do the same thing for number 14. What you need to be careful with number 14, again, is what quadrant are you in? So in this case, I'm in quadrant 2. So when I draw my triangle here, I'm going to make sure I'm aware of my directions. This is theta. My opposite is 2. My hypotenuse is 3. Pythagorean theorem, a squared plus b squared equals c squared. So in this case, a squared is 5, so a is the square root of 5. However, I'm going to the left, which makes it a negative square root of 5. And so that is the same idea as before, just what direction are you going? Be careful with the signs on those. And I'm going to do the same thing. I'm going to write down what's my sine of theta. So sine of theta is 2/3. And cosine of theta is negative square root of 5 over 3. Personally, I am not going to find tangent of theta, because notice I technically didn't use it in the last problem because I used this formula instead, which is going to make my life easier, by the way, because if I were to do tangent of theta, it'd be negative 2 over square root of 5, and I would have to rationalize. Well, I'm too lazy for that, so I'm just going to use the other formula. So if I want sine of 2 theta, it says take twice the sine of theta cosine of theta. So then it equals twice. Sine of theta was 2/3. Cosine of theta was negative 1 square root of 5 over 3. So 2 times 2 is 4 times negative 1 is negative 4 square root of 5 over 9. And that is the sine of 2 theta. Again, I'm probably going to use the same formula for cosine. It appears to be the one most students are using. So cosine of 2 theta is cosine squared of theta minus sine squared of theta. So this equals negative square root of 5 over 3 squared minus 2/3 squared. So a negative square is a positive, square square root, they cancel. So I get 5 over 9 minus 2 squared is 4, 3 squared is 9. So 5/9 minus 4/9, the cosine of 2 theta is 1/9. So we're good with that one. Again, you can go right ahead and you can do that tangent of 2 theta formula. Or I just find it easier that if I found sine of 2 theta and I found cosine of 2 theta, why not use them? So negative 4 square root of 5 over 9 all over 1 over 9. The 9s are going to cancel, and divide by 1 doesn't change the number. So tangent of 2 theta is negative 4 square root of 5. So there we are. Sine 2 theta, cosine 2 theta, and tangent 2 theta. Let's look at 15 and 16. So 15 and 16, we're asked to verify these using our double angle identities. So that's nice. It's actually telling us use the double angle identities. So it's giving us a hint. Well, we're asked to verify, which means we want to make the left-hand side equal the right-hand side. Now, I'm going to keep the left-hand side because it's not a fraction. It's pretty simple to look at. Now, the right-hand side, the problem says use the double angle identities. The problem is, well, we have many formulas for the double angle for this one. The main one we have, and we used in the previous problems, was cosine squared of x minus sine squared of x. We also have 1 minus 2 sine squared of x, and we have 2 cosine squared of x minus 1. Those are your three formulas to choose from. So when it's cosine of 2x, which one do I use is your job to figure out. Well, if I look at the denominator and I look at the left side, they both have cosines and sines in them. So something tells me I want to choose the one with cosines and sines. It just logically seems to make them look similar. So I'm going to change this one to cosine squared of x minus sine squared of x. And I'm going to leave the denominator exactly the same, cosine of x plus sine of x. So there was your double angle. We went through, chose the one we wanted based off of what the structure was. Again, well, what do? You can't really do anything on the left side right now, so we're going to leave that alone. And I can't do anything to the denominator, so I'm going to leave that alone, which tells me logically I better be able to do something to that numerator. And what I can do to that numerator is look at it as objects. Instead of cosine squared of x minus sine squared of x, I'm looking at it as a squared minus b squared, something squared minus something else squared. And that's difference of squares. I can factor it into a plus b, a minus b. So I can factor that top, cosine squared of x minus sine squared of x, that numerator into cosine of x plus sine of x times cosine of x minus sine of x. And that is extremely helpful because I created a cosine of x minus sine of x that I wanted on the left-hand side. So something tells me I am so not going to change this. Because if I look at everything else, there's a common factor on top and the bottom. And you can cross it out. So you get cosine of x minus sine of x. The left side equals the right side. It has been demonstrated, QED. So we were asked to use the double angle identities, and that's kind of your hint for the first step for that one. And also I want to try and factor in with trig ratios. So let's take a look at 16. Now 16, hopefully we can fix this quickly. Let's make that a cotangent. That's going to make this problem a lot better. So there was a mistake on problem 16. Use your double angle identities. So again, notice there's your double angle identity. Sine of 2x is twice sine of x cosine of x. Times, well, I have a bunch of sines and cosines, so I might as well change cotangent into sines and cosines. So that's cosine of x over sine of x. Now, I'm going to also change the right-hand side. I can see on this right-hand side that these two have a GCF in common of a 2. So I'm going to factor that out and get 2 times the quantity, 1 minus sine squared of x. So let's kind of go through it. The cosines don't cancel in this case. Sorry, the sines cancel because you have a sine on top and the bottom. So you have twice cosine times cosine, which is cosine squared of x, equals, well, I can see that 2 matches. That's good. So I need to create a cosine squared of x over here. Well, lo and behold, this is the Pythagorean identity. It is cosine squared of x. So we are done. So the left-hand side equals the right-hand side. It has been demonstrated, QED. Big problem with this one is make sure you adjust 16 to say cotangent instead of cosine. Otherwise, it would be a very complicated problem that actually would not work. So now let's look at number 19. Oh, this one is fun. We are asked in questions 17 through the end to solve for all of the values for x that work. Now, whenever you're dealing with these, remember, the idea is how can I make my life easier? And in this case, it goes through, let's treat it like an a, 2a squared plus 3a minus 2. And this involves the AC method of factoring. A times c is negative 4, and they add to 3. So what numbers multiply negative 4, add to 3, are 4 and negative 1. And so we would split this into 2a squared plus 4a minus 1a minus 2. And I would keep going using factoring by grouping. And I would get 2a minus 1 times a plus 2. And that's the same work we need over on this left-hand side. But rather than a, we have sines. Instead of a squared, we have sine squared. So I have twice the sine squared of x. And I'm going to still use that 4 and negative 1. So plus 4 sine of x minus 1 sine of x minus 2 equals 0. And I'm going to still do the grouping. The first two had a 2a in common. The second two had a negative 1 in common. these have a 2 sine of x in common, and that's going to give me sine of x plus 2. These have a negative 1 in common, it's going to give me a sine of x plus 2. And so I'm left with twice the sine of x minus 1 times sine of x plus 2. Now we set each one of these equal to 0 to solve. And so if I set 2 sine of x minus 1 equal to 0, we would add 1 and then divide by 2, and I get sine of x equals 1/2. Well, for our values, sine of x is going to be equal to 1/2 at 30 degrees and 150 degrees. If we do the next one, sine of x plus 2 equals 0, we get sine of x equals negative 2, which does not work. You cannot have a sine value that is bigger than 1 or less than negative 1. So my only answers in this case are x equals 30 degrees and 150 degrees. And that's it. This one I want to deal with because it dealt with the AC method of factoring. I want to make sure we are good with factoring, which you can use A's to kind of help you out. 23. So if we look at this case, what do we do? Oh, there's a bunch of approaches, and I've seen some interesting ones from students on this. Is a lot of people have chosen to set equal to 0 first, so they subtract the cosine squared of x, which is good. And so I get sine squared of x minus sine of x plus 1 minus cosine squared of x equals 0. And from here, I mean, there's just a bunch of things you can do. I've seen, and this is brilliant, students that notice this is a Pythagorean identity. And they have sine squared of x minus sine of x, and they change 1 minus cosine squared into sine squared of x. That's just brilliant. Great job seeing the Pythagorean identity there, because we can combine like terms and solve from there. If you didn't notice it, what would happen is you would change this to a, I'll do it right here, equals 1 minus sine squared of x. And you would subtract the 1, and notice that would cancel this out. And you would add the sine squared of x, which notice that would make this a 2 sine squared. So there are many approaches to this. So I don't care which one you use. I find this one to be very brilliant for using the identities. So how do I solve from here? Again, I see squareds. I'm going to look to see, can I factor? And so I'll write off to the side. I have twice a squared minus a equals 0. And I just know from a basic variable that involves GCF. So it's going to be the same thing here. I'm going to take out a GCF of sine of x and then solve. So I get sine of x equals 0, which occurs at 0 degrees and 180 degrees. And then I have 2 sine of x minus 1 equals 0, which we said sine of x you would add 1 and divide by 2, which I believe in the previous problem we had, what, 30 degrees and 150 degrees. So these are our solutions for it. So that's 23. 24. Looks like it's complicated, but it's actually a bunch of sines and cosines. So sine of x times cosine of x, and then cotangent is cosine of x over sine of x equals 1/2. So the sine of x are going to cancel. So I'm left with cosine squared of x equals 1/2. Well, I'm going to square root both sides. But be careful when you square root, you cannot forget the plus or minus sign. So you get cosine of x equals plus or minus the square root of 1/2. So I square root at the top and I square root at the bottom, which means I'm going to have to rationalize. So that's going to give me cosine of x equals positive or negative square root of 2 over 2. So I have to look for both of these in my cosine column. And so when we're dealing with number 24, we have plus or minus the cosine, well, plus or minus radical 2 over 2 for cosine. We're going to have a bunch of numbers for this one. We are going to have, for positive radical 2 over 2, you get x equals 45 degrees, and you're going to get x equals 315 degrees. For negative radical 2 over 2, you're going to get x equals 135 degrees, and you're going to get 225 degrees. So I actually have 4 answers in this problem. Let's look at 25. Well, this one's weird because it has a double angle here. Again, so I'm going to use that idea. If I have a double angle, I'm going to change and apply my formula. So I have 2 sine of x cosine of x minus sine of x equals 0. Now we've dealt with these before. Notice they both have a sine of x. So I am going to take a GCF of sine of x out, and that's going to give me twice cosine of x equals 0. Set each factor equal to 0 to solve. So sine of x equals 0, that occurs at 0 degrees and 180 degrees. Twice the cosine of x minus 1 equals 0. You would add 1 and you would divide by 2. And so I need to find out where is the cosine of x equal to 1/2, and that is at 60 degrees, the first quadrant, and at 300 degrees in the fourth quadrant. So this would involve GCF of factoring, like we've done before. Last, it is 26. And again, wow, look at that. I have a tangent squared and I have a tangent. Something tells me that it's going to follow a GCF factoring approach. So I'm going to take out a tangent of x, and I'm left with tangent of x minus square root of 3 equals 0. Set each factor equal to 0 to solve. So tangent of x equals 0. That occurs at 0 degrees, and it occurs at 180 degrees. If I have tangent of x minus square root of 3 equals 0, I get tangent of x equals square root of 3. And that occurs at 60 degrees, and it occurs at 240 degrees. So there are my 4 answers. And kind of talked really fast at the end. Hopefully you can go back and you can go through the video and go through. I mean, 47 minutes is a long time. But that really covers half of your review on it. So hopefully this gives you an idea of what is on the test verbatim for it to help you out.